And now we have a workshop of AI, Trustworthy AI, Overcoming Bias, Enhancing Explainability, and Managing Risk. And I want to welcome Lovell Hodge. Did I pronounce that correctly? Thank you. Okay. Ph.D. Head of AI, BMO, and Wealth Management. All right. Well, welcome.
Thank you very much. Okay, I know what you're thinking. It's 5 p.m. This better be good. Let's see what we can do. All right. So I'm here to talk to you tonight about trustworthy AI. And, you know, this is a big topic now because of generative AI. It actually wasn't that big a topic before. Important topic, but it didn't take off as much as it is today. And that's because of the advent of generative AI. So what we're going to do today is we're going to look at why this is important. We're going to look at some techniques to mitigate risks. And we're also going to get a little technical, which is going to be a little bit of a different presentation to the ones that you've seen before, because I'm going to dive into the Gen AI models a little bit and just show you what's going on, and then we'll understand where this issue could come from. So we're going to start with a fundamental statement here, which says, for an AI system to be trustworthy, it must be functionally reliable, free from bias, and support explainability. A lot of words there. But essentially what I'm doing is laying the groundwork for, let's just be on the same page. These are the three things that we need to agree on, that it has to be reliable, it has to be free from bias, or at least minimum bias, and support that transparency. In other words, not have that black box characteristic. So we can sum these up in three words, right? Reliability, non-bias, and explainable. And for reliability, what we're really talking about is when you use the models, you get a consistent outcome, something that you can rely on from a performance perspective. And we're actually used to that when we talk about traditional machine learning, because when we build models, logistic regression models, et cetera, we sort of understand how they work, and we understand what that output should be. And most times we get it to perform the way we expect it to perform. But in Gen AI, it takes a different twist, and we'll see why. The non-biased side says it has to be fair and ethical. So in other words, it shouldn't give you responses that are biased against race and ethnicity and all that other stuff. And that's actually a fairly difficult problem to solve. And it has to be explainable. So we have to be able to say, well, maybe to the government, or if you're a highly regulated industry, this is why the model actually produced this outcome. So these three things constitute what we call trustworthy AI. Now, on the other side of the fence, we have something called rogue AI. And if you have rogue AI, then what you really have is models that have what we call hallucinations. And essentially, they make stuff up. And not necessarily, what the outcomes are not necessarily grounded in fact, and potentially are unreliable because you can get different outcomes for the same input. Bias says, well, it could be unfair or discriminatory in some way, and the decisions or output reflect a bias that might be inherent even in society. The black box approach, and this is extremely an extreme problem with generative AI, is we have these outcomes that we can't necessarily explain. And by the way, it's not only that we can't explain the outcomes, but the outcomes may change as time goes on. So it complicates the problem. So essentially what happens is you have this tug of war happening. You have trustworthy AI on one side and rogue AI on another. And the reason why I depict this as a tug of war is because it's constant. It's not that you build a model and say, I've solved for trustworthy AI, and so off I go and I can go to dinner at 5:30. What can happen is the model can perform for a period of time, and then all of a sudden you can get hallucinations, or you can get bias, or you can get black box characteristics, surfacing, depending on what you're doing with the model. So this problem is actually, you can think of it conceptually as a constant battle, a constant tug of war. Now, there are some examples, famous examples of this stuff, and I'm just going to go through three of them real quick here. So Morgan & Morgan versus Walmart. Morgan & Morgan is a personal injury law firm in the US, and they were preparing for a case for their client against Walmart, and they used generative AI to do their research around cases that act as precedents. And it turns out that the AI actually hallucinated and presented the lawyers with cases that actually did not exist. So when these cases were cited to the judge, it was revealed that these cases were not exist, and the lawyers really got into trouble. So what that did, it really raised questions about the applicability of AI in certain fields like law. And by the way, law actually stands to benefit a lot from Gen AI because of the reams and reams of unstructured data that could potentially be summarized and processed through generative AI techniques. But this particular problem of hallucinations plagues the industry. Another example where we talk about rogue AI is discrimination in AI hiring tools. So, for example, Amazon has been hit with this, as well as some hiring firms in Australia, where they showed bias against non-native accents. So, for example, you send a video in, you're asked to send a video of yourself, you have an accent, some other accent that's not the norm among the majority, and the AI says, nope, candidate is no good because they have an accent. So there's a lot of increasing regulatory scrutiny around the use of AI tools in these sort of automated processes. And again, this is a really important point for the industry. Now, the last example I'm going to show you is the risk of opaque decision-making. And this is essentially very important for financial institutions that are highly regulated. Imagine trying to, here in Canada, explain to OSFI why someone was denied for a mortgage or why someone's transactions on their credit card was denied, and you're not able to actually explain why. Because the model output, you can't trace it back to anything that you can recognize. So AI systems often flag transactions without transparent explanations, and financial institutions can face potential fines for this. Because of the regulations today, especially amongst automated decision-making, and especially in places like Quebec that have even more stringent laws around the use of AI and automated decision-making systems. So, why does this happen? Well, the answer is complicated, but I'm going to try to explain this before you have to go for dinner. And the reason why this happens is, in generative AI, we use something called a transformer architecture. This was invented by Google back in 2017, and it looks like what you see on the screen. And the interesting part of this is that the knowledge that is enveloped in this architecture is actually in the form of matrices. And these matrices occur in different parts of the architecture, but there's no clear rule base, there's no database of facts that you can program or can be learned by the architecture. All of the knowledge within this model is essentially what we call statistical associations rather than grounded, interpretable reasoning or verified facts. In other words, it's a bunch of numbers. And so if you look at the screen, this whole concept of data or information or knowledge being represented by matrices. If you remember your linear algebra days, I'm sure you want to forget them, but those days were important, believe it or not. All of the knowledge that is essential to the model is actually coded in matrices. And that presents a problem for a number of reasons. It works well, but it also has its shortcomings. So what are these shortcomings? Well, they don't store facts, like I said. They encode patterns in language as billions of weighted connections between neurons. And that's what we call a deep neural network, which is essentially the sort of core of this transformer architecture. So when an LLM is working, what happens is the data comes in, and the LLM essentially predicts, it starts a sentence and predicts the next word through a statistical sort of learned pattern that has learned through association in its training. And so that this prediction of the next token, if it has multiple tokens that are equally probable, it'll just take one at random. So what that does, it causes some of this output to be non-deterministic. We can't actually predict with certainty what that output is going to be. And this is why it's called a non-deterministic type model. Now, the other problem is that these LLMs have been it's called GPT for a reason, because it's generated pre-trained, and that pre-training is actually using publicly available data off the internet. And unfortunately, inherent in that data are biases, which we see every day. In fact, not only are there biases, but because we're training the model with data in a concentrated form, these biases are amplified in many situations. So you give these three issues legs to stand on, and they manifest themselves in things like hallucinations, bias, and of course, because of the architecture, you don't have that clean way of explaining why the model has output what it did. So here's an example of something that I've actually done myself. So I've asked ChatGPT, is 3821 a prime number? And it says, no, 3821 is not a prime number. It is divisible by 43 and 89. But if you multiply 43 and 89, you actually get 3,827. So ChatGPT is predicting the next token. It doesn't know for a fact. I actually asked it not to use an external calculator and all that stuff. But if you were to ask it just in its native form to do this, it struggles. So it doesn't really know the answer, so it just predicts the words for me. And that's where you can get into trouble. It's hallucination. Another example is, if you think of LLMs, because of that matrix formulation, it is a black box. You can't read the numbers and come to some conclusion as to where this knowledge came from. So that's that black box. There's no reasoning pathways that you can easily see. So what we have here is something called rogue AI, which is caused by those issues that I just described. And hallucination, essentially, is caused by next token prediction. It could be caused by incomplete training data as well, and that's pretty common, and lack of external verification. Unless you're really verifying the output of the model, it's very easy to fall into the trap of believing what the model is telling you. Bias. If there's bias in your training data, then, or imbalanced representation in some way, so for example, they'll say, well, most doctors are male, and you don't talk about female doctors, that's an imbalanced representation, and that is amplified by the model. And of course, because we train some of these models with reinforcement learning and human feedback, that's what that RLHF is, that can also have bias inherent in the process, and that can attribute to the behavior of the model. So the black box situation, when you talk about data that has high computational complexity or high dimensional complexity, meaning data from all sorts of sources, the web, et cetera, that's a high dimensional complexity data. And because we're representing all of that knowledge as weights in a matrix, we don't have a way of really looking at a pathway for reasoning like a rule base would. And that's why the explainability is a bit of a challenge. So we have to address these problems. And there's been a lot of work in trying to understand how the data is represented, and we come up with mechanisms for mitigating some of the risk associating with hallucinations, bias, and of course the black box characteristics. We've talked a lot here about RAG, retrieval augmented generation. One of the things I will share with you is that RAG is a fairly fundamental concept. I'm not going to go into it too deep here, but what you may not have heard today is that the RAG architecture is not the most important part of this pipeline. It is how you retrieve the data that's the most important part. So the way it works is, when you talk about a RAG pipeline, you take some documents which you want to process, you chunk them out, and you embed them. I'm not going to go through all the details, but you embed them into something called a vector database. Now, when you prompt the model to ask a question about your documents, what the model does, or the system does, it takes the chunks that are relevant to your question, couple it with your question, and sends that to the LLM. So it gives it context in which to answer the question. So if you don't retrieve the right chunks of the data to couple with your question, the model could be misled. And the model will hallucinate on top of that as well if you don't prompt properly. So retrieval augmented generation is a good way to mitigate some of that hallucination, but it is not perfect unless you improve some of the retrieval capabilities that are in the pipeline. all right? Very important. And in order to, as an example of that, there's a lot of different techniques that we use for improving retrieval. Knowledge graphs, chain of thought, topic modeling, even AI agents. You want to go out and grab some information from a database somewhere, you would use an agent to make sure you get the right information. These are the types of things and investments we're doing in ensuring that that retrieval of the information actually is efficient and optimal. Okay, with me so far? Okay, I don't see anyone with their head on the table, so that's good. I'll take that. Now, another way of addressing hallucination, you'll say, well, wait a minute here. We don't store all our data in vector databases, so what happens then? Well, this is where all of this hype about agentic AI and agent AI comes into play, because what we can do is we can build agents that actually know how to access information from various sources. And if you know how to access information from various sources and process it efficiently, then you can use a wide variety of source information in order to prevent hallucination. And keep in mind, the hallucination here is because the model is depending on its own knowledge and its own weights. If we bypass that and give it the knowledge it needs, then we can mitigate this issue of hallucination. Now, we also have to talk about bias. We use pre-trained LLMs in our companies, but we have to make sure that those pre-trained LLMs are not biased. And the way to do that is we have certain bias evaluation data sets that we can use to measure how much bias there is in the actual LLM. And if we know how much bias there is, then we can actually change the weights slightly to mitigate some of that bias inherent in the pre-training. And so what happens is we adapt the LLM in order not to have the bias manifest itself, and we inject what we call specific weights called adapters. And these adapters are added to the LLM to reduce the bias because they're under our control. I'm going to talk a little bit about how that's done, but before we do that, let's talk a little bit about some of the data sets. So they have different data sets out there, but one of them is StereoSet, for example. It measures stereotypical bias. And some of the things that it can do is you can ask it'll ask questions of the LLM to say, is this a stereotype? Is this an anti-stereotype? Or is this a neutral statement? So you see here, women can't drive as well as men. That's a stereotype. It's actually not true. Women are excellent drivers. That's an anti-stereotype. So you're going way beyond the norm to sort of not be stereotypical. And then, of course, neutral, women enjoy driving. So if the LLM can differentiate the stereotype embedded in these sentences, then you get a measure of how much bias there is. Now, obviously, there's different types of data sets, but you get the point. So once we understand how much bias is in the LLM, then what we want to do is adapt the LLM to get rid of that bias. And we use something called LoRA. LoRA stands for low rank adaptation. I could spend an hour up here explaining single value decomposition and all that stuff, but you'll definitely have people heads on the tables. But I think that the key point here is that if you represent remember those matrices I talked about, if you have a representation of the most important data within those matrices, and you can tweak them slightly, then you can focus or target training on those weights to remove the bias. And that prevents you from having to retrain the entire model. So this is called LoRA. And don't worry about the math, I just put that on there to impress you. But essentially what happens is you're debiasing the model, okay? It's a basis for different, what we call parameter efficient fine tuning, and it's called parameter efficient because it's an efficient way of programming these large language models. So AI models generate responses based on learned patterns, but how they arrive at answers can also be unclear. Explainability techniques help us visualize, interpret, and audit those AI results. So now we want to peer into the model and ask ourselves, well, how is the model arriving at these answers? And so what we can do is we need some way of visualizing what's going on behind the curtains. And this is to get rid of the black box characteristics of the model. Because remember, the hallucinations, the bias, and the black box, they all contribute. If we can de-risk the model, if we can reduce that stuff, then we're heading more towards trustworthy AI. So for explainability, we focus on two outcomes. What's the model focusing on? So you give the model data, what in that data is the model actually focusing on? And then the other piece is, well, how is that focus influencing the answer? If you know those two things, you can either retrain the model, change the data, or you can take some action to either change the behavior of the model or at least explain its outcome. And that's where these techniques get in. So one of them is tracking what we call attention maps. There's actually a very important part of the model called self-attention. And this, what it really does, it says, look, if you give me a sentence, I'm going to focus on certain parts of that sentence, and the pieces that I focus on will influence my outcome. So if you say the fox jumped over the moon, I might think about the fox and the moon. Those are the things I want to focus on. And I may say, a model may say, well, that's not possible because I focused on the fox not going to jump over the moon. But at least it knows what to focus on. And so by visually understanding that focus, we can understand the outcome. And so we have these attention maps that we can produce. These are libraries that you can download and use in your code. And those allow us to peer inside this black box topology. The other one that's one of my favorite, actually, is called SHAP values. It's Shapley additive values. Essentially, what happens is it takes components of your input, and it shows you how those components are influencing your output. So in this situation, you have a sentence that says, I love you, you are so wonderful, I think you're boring. Normally, you wouldn't put those things together, but if the model says this is a positive sentiment, you might want to know, well, what's really contributing to that sentiment? And so if you look at the Shapley additive values, then what it's saying is the I love you, the love essentially, and the wonderful are the things that are contributing most to the fact that it's labeling this as a positive sentiment. Given this information, you might be able to explain why someone's mortgage might be denied, or why it said that a call was terrible between a client and the call center. But at least you have a mechanism to which to peer behind the black box and essentially understand what is causing or at least contributing to the output. So I want to leave some time for questions and discussion because this is an important topic. So I try to go through not too fast, hopefully, but fast enough. So trustworthy AI must be reliable, it must be unbiased, and it must be explainable. Now, the techniques that I talked about are not perfect by any means, but they are a start. And there's a lot of research that's actually happening, especially with the Gen AI transformer models around these specific things, reliability and bias and explainability. And the reason for that is because these models are not going to be able to be used in certain circumstances, especially in highly regulated industries, with certainty, unless we have tools and techniques by which we can mitigate these risks. So when we talk about trustworthy AI, the bar for me is these three things. It must be reliable, it must be unbiased, and it must be explainable. If we do come across rogue AI, with a risk of hallucination, bias, and certainly black box characteristics, then we have to rely on the tools we have and those that are under research to mitigate those risks. So what we did today was we explored a few things. We explored using the RAG pipelines and AI agents, and this really reduces hallucination by focusing the model on the context and information that we have at our disposal and removing the dependence of the outcome of the model on the weights that are inherent in its matrices, or knowledge that are inherent in its matrices. That's a good thing because you're moving from a non-deterministic to a more deterministic outcome. The second thing is bias evaluation and LoRa. If you remember one thing today, remember LoRa. It's easier, just a name, right? Low rank adaptation. So bias evaluation and LoRa identify and mitigate those embedded biases, and then we use the explainability tools to peer behind the curtain to understand what's going on. So with that, I want to leave you with a final thought. Building trustworthy AI is a continuous process. It cannot be said that you build a model and you're done. You have to constantly monitor it and for bias and use all the techniques you can to ensure that your model ultimately is trustworthy. So we combine the model design, the evaluation, and transparency tools to align the outcomes with performance, the ethical and behavior, and social expectations. So with that, You can take a snapshot of this. I just want to give you some resources if you want to read up more on this stuff. I wanted to leave a few minutes, but yeah, I think I'll wrap it up there. Thank you. And we have a few minutes, so yeah, I think we have some questions.
Thank you so much. An excellent talk. Can you comment about something called prompt injection? How do you test and create model to mitigate the risk of people trying maliciously attack your bot?
Yeah. So basically, this is a very interesting question. So basically, you start with prompt injection, right? So what happens is an attack on the LLM. What you're really trying to do is does anyone here familiar with the concept of SQL injection? Right? Okay, so just for anyone who isn't, when you have a website, what hackers do is they inject information into your website, they put it into your inputs, but it's SQL, so the back end takes that SQL and runs it as if it was just normal text, and you can essentially get access to the system. So it's SQL injection. The equivalent of that is called prompt injection. So what happens is you have an LLM, and you by giving it specific prompts, you elicit certain behaviors from the LLM that are, by necessity, unwarranted. So what that means is you can prompt the LLM to behave in a certain way that gives it very, I don't say very bad behavior, but it certainly gives you more control over the output of the LLM. In a RAG situation, it's a consideration because what happens is when you create a RAG pipeline for your organization, if you don't control the behavior of the LLM, or at least abstract the user from controlling the behavior of the LLM, you could be susceptible to prompt injection. And that could be very bad for the organization. So it's a very good question. And some of the ways to do that would be to use a library of prompts. You're only really limited to these types of prompts. Or you can have what we call a triage LLM that says, hey, this prompt is not within the parameters that we defined for use of the system, so I'm not going to let it go back to the real LLM in the background. So there's techniques to mitigate the risk, but it is a very, very important point you bring up. Any other questions?
There's one.
Okay. There's one more.
So, hi, this is Dennis. So from the morning, we've heard, there's not been a session where we've not heard about AI. So AI has pretty much been dominant in all those conversations, right? How do you see AI 5 years from now?
I should put that into ChatGPT and see what it comes up with. Look, every technology goes through phases. The phase right now where I think everyone's interested in is agentic AI, and it's interesting because I was sitting and listening to a lot of the talks about agents and AI, and I remember even as a Ph.D. candidate working on multi-agent systems. And so the topic is not new. I'm not that old, by the way, but the topic is not new. But I think what is new is the capabilities around compute, right? Computational power, and certainly some of the architectures like the transformer architecture. So why am I telling you this? If you look 5 years from now, I think what we have done is we've reached a basis for capability with the transformer architecture that will accelerate the growth of AI. So because we've reached that point, it's easier now for us to make stuff that is more intelligent more quickly. And so agentic and agent-based AI is the new fad today. But tomorrow, I would see us getting into a situation where agents become a lot more intelligent, and there's an architecture that supports that intelligence based on the transformer architecture, but better than it. Because one of the problems that the transformer architecture has is it needs a lot of data to work properly. And I think that ultimately where we're going in the next 5 years is to use less data smaller models, much more efficient models, and that will propel us at an accelerated rate towards more agentic AI. That's my basic and humble prediction, but I think that's where we're going.
All right. So-
Okay, I think we have one more. Do we have time for one more? Take a vote, one more? Is that okay?
Okay.
Oh, okay, sorry, yes.
Great. Przemek Tomczak from OSINT. Just a quick question. To accomplish what you outlined, are you hosting the training yourself, the inference yourself to have that control and fine-tuning, or are you leveraging what's already out in the marketplace?
So it's a great question. So the LoRa side can be done in-house. You can do it because it's Ph.D., it's parameter efficient fine-tuning for a reason. You can do it in-house, and certainly my teams have done it. The other piece of good news I'll leave you with is that most of the ChatGPT, Azure OpenAI services, et cetera, they actually provide you capabilities to do that. So everyone recognizes that you do have to fine-tune and all that, so they do provide the libraries and frameworks to do that. Yeah. Okay?
All right. So I want to thank you very much. You were very technical sound, and you created a great story. I was very passionate about all the learning that I had with you today. I didn't even know that chat could be used for LLMs.
Yes.
So great. Like you live for the expectations of the 5 p.m. Thank you very much. It was
All right.
a great talk.
Thank you.
Ooh.